Live from the BBC, The Naked Scientists.
Welcome to this week's edition of The Naked Scientists with me, Dr. Chris Smith, and with Dr. Phil Rosenberg.
Hello.
Tonight, we're zooming in under the microscope on the science of the very small. We're talking nanotechnology, in other words, miniaturising science. What can nanotechnology do for us? Could it revolutionise healthcare? Will we be able to track tumours and get rid of them from the body? What about zooming in and seeing them working at a cellular level? Can DNA provide us with faster microchips in future? In other words, turning microchip manufacturer into a PC of cake, if you pardon the pun. Well, to help us to answer all these questions tonight, we have from the University of Surrey, Dr. David Carey. Good evening, David.
Good evening, Chris.
We have from University College Dublin in Ireland, Donald Fitzmaurice. Good evening, Donald.
Good evening.
Neil Morgan's dropped in from Cambridge University. Hi, Neil.
Hi.
And Stephen Webb's here from Daresbury Laboratory in Warrington.
Hello.
So we have some of the finest minds to talk nanotech to you this evening. If you have any questions about the science of the very small, give us a call now, 08459 25 2000, or email me, chris@nakedscientist.com. But that's not all that's in store for us this evening. Phil, what else you got up your sleeve?
Okay, also today we're going to be talking about, or I'm going to be telling you about a new space telescope that's been launched by the Japanese Space Agency. And Chris is going to be talking to James Clark at the University of Washington about a recent dinosaur discovery.
Quite literally the origin of Tyrannosaurus rex. We'll also be heading over to Astley Cooper School to find out about the science of gravy. Derek and Dave are cooking up something exciting for you in the kitchen. What happens if you look at gravy down a microscope as it cooks? Why does your gravy thicken? They've got the answer. That's coming up very, very shortly. And up for grabs this week in our competition, Science Fact or Science Fiction. That's easy. We give you a couple of easy science facts and you have to tell us whether they're true or not. Then all we have to do is give us a ring, 08459 25 2000. You could be heading off to Kew Gardens because we've got tickets to give away for that. That's 08459 25 2000, or email me, chris@nakedscientist.com.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
Up first this week, just let's have a quick chat to Phil. Tell us about this science of your Japanese telescope.
Okay, now there's a new telescope just been launched this week by the Japanese Space Agency. It's actually partly developed by the European Space Agency as well. And now, just like the Hubble Space Observatory that's up there at the moment, we need to launch these things up above the Earth's atmosphere so we can get a better view of space without the atmosphere getting in the way, clouds and absorption from the atmosphere. Now, the big difference between this JAXA observatory called Astro-F and Hubble is that Hubble looks at stars and galaxies in visible light, so the same sort of light that our eyes see, whereas this Astro-F is going to be looking at infrared light. Now that's really quite exciting because we can see a lot of different things used infrared compared to visible. Now one of the big things is it can look at newborn stars. Now when a star first forms out there in the universe, usually it does so in a big cloud of gas and dust, and that dust obscures the normal visible light coming between this new star and the Earth, so Hubble can't see it. But infrared light actually goes straight through the dust as though it wasn't there, and the Astro-F telescope will hopefully then be able to see these stars in the process of actually being born and being created. Now that in itself is pretty fantastic. Also, it might be able to see and look at nearby stars and actually see within the dust possibilities for locations where new planets could be forming around new stars. So again, fantastic science going on. We're also going to be looking at very, very distant galaxies, billions of light years away, which actually allow us to penetrate and look at the early universe. Now, because light takes a certain amount of time to travel, it actually travels 1 light year, the distance 1 light year, in 1 year. That's how you define a light year. Now, we're going to be looking at galaxies billions of light years away. So we're going to be seeing light that was emitted billions of years ago, right near the beginning of the universe. And that's going to give us a really good idea about how galaxies form and how they evolve over time.
I've got a question here for you, Phil, whilst you're talking about telescopes and things. This one's from Puerto Rico, and it says, Dear Naked Scientist, greetings from Puerto Rico. I listen to your podcast at least twice a week, just in case I don't get something the first time. English isn't my first language, but I can't wait for the next one each week. A simple question. Down here in Puerto Rico, we're supposed to have the largest radio telescope in the world. Is that true? And in fact, how does a radio telescope actually work? That's from Ernesto Rodriguez, who's in Puerto Rico.
Yeah, that's absolutely true. The biggest radio telescope in the world is the Arecibo radio dish down in Puerto Rico. Now, essentially, they work pretty similar to a normal telescope. But if you look at them, they don't look quite the same. Actually, if you've seen the James Bond movies, you'll have maybe spotted this.
Yeah, he was dangling off of the sort of central core frame, wasn't he?
Yep, they look just like a really big satellite dish, really, that you get your satellite TV from. And they work in essentially the same way. The white surface that forms the big bowl, the big dish, acts just like a mirror with normal light. It reflects the radio waves up to a detector in the centre, and that detects, that essentially forms an image, focuses the radio waves, and creates the radio image that we see, that we can look at galaxies with. But it's also got the added advantage that actually we can do sort of radar pings in the same way, say, a speed trap would catch you in your car, but on a massive
speeding
scale.
Aliens.
Yeah, absolutely.
Like UFOs that are breaking the speed limit or something.
Well, maybe not quite that. But we can actually send radio pings out to other planets. We can actually ping radar off Saturn or off moons
to see
of Saturn.
how far they are away and things like that.
Well, there's also an advantage that you can actually see speeds using the redshift, Doppler shift of the radio waves. So, for example, if you fire a radio beam at, for example, Mercury, you can actually see that light that's bounced off one side is actually altered compared to light that's bounced off the other side because of the way that the planet is spinning. So in that way you can see how fast, for example, Mercury is spinning just by looking at the radio waves that we can bounce off the planet.
Well, sticking to the space science theme, it turns out that Pluto is celebrating this week, if it could indeed celebrate, because it's got 2 new moons. Pluto has long been known to have one moon, and it's called Charon, and it's a very big moon. But a couple of scientists called Alan Stern and Hal Weaver, who are working over in the US, used the Hubble Space Telescope, and they've published in this week's edition of the journal Nature their first discovery of these 2 brand new moons. They haven't got a very exciting name yet. They're called S/2005 P1 and P2. But they're about 30,000 miles out from the centre of Pluto on this orbit. They're on the same kind of orbit as Charon. And what the scientists think this tells them is that they probably formed at exactly the same time, and where they think they came from was that another Pluto-sized planet probably smashed into Pluto when it first formed about 4.5 billion years ago, and the debris that produced has now formed these 3 tiny moons. The way they discovered it was to shine or focus the Hubble Space Telescope onto Pluto and then look for a very long time, but also then turn up the gain, in other words, brighten the picture as much as possible. Now, obviously, Pluto and its big moon, Charon, which reflect a lot of light, showed up very, very clearly. But then, in the background, these 2 tiny pinpricks of light winked into view, and that was these 2 new moons. Now, the guys are going to go back on the 2nd of March and check that this is a very real finding, because they're pretty sure they haven't missed any moons, and they're sure it's a real finding, but they want to, just to make sure they haven't missed anything. So they're going to go and have another look. And another interesting little juicy tidbit that came out in January was that NASA's mission New Horizons was launched as well. And this is a probe which is a fully or computerized, robotized probe. It's actually the fastest spacecraft ever created, and it's going to zip along to Pluto. It's going to take 9.5 years to get to Pluto, but when it does, it's going to start exploring that very exciting area of our solar system. It's 6 billion kilometres out there. It takes 6 hours for light from the sun to get to Pluto. It's an incredible distance away, and to put that in perspective, light only takes 8 minutes to get to the Earth from the sun. So it's an incredible distance. We can't go and see for ourselves what's going on out there. We need to literally send something to go and have a look for us. But why this is important is because it will shed a lot of light, if you excuse the pun, on that very unknown part of our solar system, a dark area in our knowledge at the moment, because out there somewhere are all these objects, the Kuiper Belt objects, which formed in the early days of our solar system, and there's a lot of stuff knocking around which we don't know about. Wouldn't you go along with that, Phil?
Yeah, absolutely. I mean, Pluto's really quite an unknown object. Most of what we know, or a lot of what we know about the outer solar system, came from the Voyager spacecraft. And they actually missed Pluto. The alignments weren't quite right for them to go past Pluto. They went past Jupiter, Saturn, Uranus and Neptune. But Pluto just wasn't possible to get to. So, yeah, absolutely. Brand new science coming out of this.
So, Naked Scientist, Dr. Chris, Dr. Phil, we're here with you until 7 on BBC Local Radio right around the eastern counties. If you have any questions for us, anything on anything, we'll just insert it into the show here and there, 08459 25 2000, or you can email me, chris@nakedscientist.com. Now let's catch up with Jim Clark, who's over in the States. Good evening, Jim. Hello, Jim.
Hello.
Now, you've been out in China looking at some interesting things to do with dinosaurs. Tell us about your work.
Well, for the last 5 years, I've been working with Dr. Xu Xing of the Institute of Vertebrate Paleontology and Paleoanthropology in Beijing, and we've been going out to Xinjiang in the Gobi Desert of far western China. And our most recent discovery is a kind of an ancestor of T-Rex, a thing we call Guanlong.
It's a nice name, but what does it actually mean?
It means crested dragon.
And was it a crested dragon?
Yes, well, it has this big crest running down the top of its head, which we were surprised to find once we dug the skeleton out.
Why is this so important?
Well, for one thing, it's very, very old. So T-Rex was about 65 million years old, and we're at about 160 million years old. So we're older the other direction from T-Rex than T-Rex was from us.
That's a significant difference, isn't it? Because 60 million years ago is roughly the time when the dinosaurs were thinking about being hit by a meteorite and disappearing for good. 160 million years must be way back in the really early origins of T-Rex.
It is. It's really when the dinosaurs first started going, when the first big dinosaurs appeared.
So what big unknowns does this fill in the field?
Mainly it helps us kind of verify that T-Rex and the Tyrannosaurs were relatives of the kinds of dinosaurs that were giving rise to birds, and that the timing of all that is really back there at the beginning of the kind of surge of dinosaur evolution in the Jurassic.
So, given that this early dinosaur is a sort of stepping stone from other dinosaurs into the T-Rex, what became the T-Rex lineage,
right.
Can you just set the scene? What would he have looked like if we could do a sort of walking with dinosaurs effect on him? What would he have been like?
Well, fairly gracile animal. Unlike T-Rex, it had long forelimbs, so that's one of the things that's placing it with these theropods that are giving rise to birds. Guanlong wasn't terribly big, but it wasn't terribly small, so it was about 12 feet long from toe to the end of its tail. Well, we're guessing that it was a fast, agile animal, but of course that's something you don't really have a good handle on with fossils.
Because one view is that Tyrannosaurus rex wasn't agile, he was quite lumbering. Right. Is that a reasonable thing for people to assume?
There was some very good work that was done based on basically how big the muscles would have to be on an animal as big as T-Rex to move it quickly, and basically they couldn't find any way to put enough muscles on T-Rex to move it very quickly. So that's not the case with our thing. I mean, ours is smaller, so ours could have been faster. But again, I mean, this is all fairly speculative.
Very early and not recently or not before seen, it's come from an area of China that hasn't been looked at very, very closely for dinosaurs, isn't it?
Well, there was some really interesting earlier work. A joint Canadian-Chinese group was out in the 80s, the late 80s. A fellow named Phil Curry from Canada was one of the co-leaders. Dale Russell was one of the other co-leaders. And they found some intriguing things, but then that was right at the end of their expeditions. And Phil has told me that's the one place he'd really like to go back to explore for more fossils in China.
And where will you be taking this research next?
Well, we're continuing to work. We're continuing to study the fossils we have found. So, I mean, there's just a huge area out there. This is the area that, in the movie Crouching Tiger, Hidden Dragon, the beautiful Badlands that you see there, that's the area that we're working in, and they go on for, 100 kilometers or so. So there's just a huge area to look for. Because
presumably you'd like to fill in the gap between 160 million years and the 60 million years to the modern tyrannosaurs.
Well, you'd like to. I mean, we're, of course, committed to these beds right now at 160 million years. I mean, I've worked in some younger beds before, but I really am liking working in these older beds. You're really getting down at the base of a lot of interesting lineages and things.
James Clark, thank you very much.
Okay.
That's James Clark, who's the Associate Professor of Biology at the George Washington University. It's Dr. Chris and Dr. Phil here live as the Naked Scientist this evening. We're taking your science questions on anything scientific. And if you'd like to give us a call, 08459 25 2000, or you can email me, chris@nakedscientist.com. Remember, we're talking nanotechnology later tonight. We have in the studio David Carey, Donald Fitzmaurice, Neil Morgan and Stephen Webb, and we'll be essentially focusing in on the science of the very small. If you have any questions for them, call now because they're coming up very, very shortly. 08459 25 of 2000 right. Now it's time to head over to Hertfordshire, where Derek and Dave are at Astley Cooper School in Hertfordshire with Craig, Lewis and Ian to help them unravel the science behind why gravy thickens. Good evening, Derek.
Hi there, and welcome to Astley Cooper School in Hemel Hempstead. And we have actually moved the Naked Scientist lab to the school today, and we'll be cooking up some very fun science right here in the lab today. And in fact, we've already been cooking up some fun science as well. So more on that in a moment. Of course, Dave is with me, as always, my Naked Scientist colleague. So please tell us more. What are we doing today?
Well, Derek, today we're going to be trying to find out why gravy thickens as you cook it.
Excellent. So this is a common kitchen effect that you've probably seen. You've probably done it at home, or you've seen someone in your kitchen doing it. We're going to be explaining why. Also with us are some students from Astley Cooper School. So could I get you to introduce yourselves? Just give me your name and what year you're in, please.
All right, I'm Craig and I'm in Year 12.
I'm Louise and I'm in Year 12.
I'm Ian, I'm in Year 12.
That's great stuff. OK, well, we, as I said earlier, have already been doing this experiment, so it's all ready for you to listen to the effects of. And Ian is the man who's actually been heating some stuff for us. So, Ian, can you tell us firstly, what have you been doing here?
Basically, we just started with some water, started boiling it up and heating it. And then we took some corn flour, and then we combined the two and just carried on stirring and heating it until it thickened. And eventually, we got some gravy-type liquid.
Yeah, OK, and it has gone very viscous, hasn't it? And I suppose it took a while, didn't it? But, yeah, how long do you think that took?
About a couple of minutes, probably.
Well, thank you very much for doing that. The question is, of course, we want to know why. I mean, have you got any idea why that happened?
Not really. I don't know why it worked.
Lucky for you. That's why we're here, basically. So, Dave, then, what we want to know is why is this gravy-like stuff, the corn flour in water that's heated, why has it gone thick?
Well, yeah, Derek, it doesn't actually have to be corn flour. Many different kinds of flour will thicken soups and gravies and things. So what we've got over here is we've got a microscope looking at some of this corn flour, and we're going to try and find out what happens when we heat it.
So then, basically, Dave has set up here a microscope which he's fixed onto a television, OK? And Craig and Louise, who are here, are going to be helping us describe what's happening down this microscope. And because we've wired it up to this television, it's very easy to see. So, Dave, what exactly have you set up?
Well, all I've got is a very little bit of corn flour, a bit of water, and on a slide and under a cover slip, so we can see what's going on.
OK, so looking at the screen then, Craig, could you just describe, what does the screen look like at the moment?
You can just see loads of small corn flour particles.
So, yeah, so we can see lots of small dark particles just kind of spread out all over the field of vision. What are they actually, Dave?
Well, corn flour is made up of little tiny lumps of starch, and so we can see all these rather irregular lumps of starch all over the microscope screen now.
OK, then now, what do we do next?
I'm going to heat this with basically a hairdryer and gently heat it and see what happens.
Now, is this like what we do when we make gravy?
That's the idea, just like what we're doing when we're making the gravy, but we can see what happens.
OK, Dave, let's go for it. OK, and Louise, can you tell us what you see then?
Particles are like joining together and kind of exploding.
OK, and when you look at what one individual particle on the screen has done, I mean, how's it changed?
It's got a lot bigger.
Does it look different? They were kind of dark, weren't they?
Yeah, you can't see them as well now.
Yeah, exactly. So what we've got now, we did have kind of these very distinct particles on the screen, but now it's kind of spread out and gone really rather transparent, or translucent at least. And so Dave's going to tell us exactly what's happening there.
Well, starch is basically a really, really long molecule. The little grains which you've seen before, basically like really tight balls of string, all wrapped up really tightly. And normally they stay that way. If you heat them up, when you heat something up, everything starts to wriggle around, and the water can get in amongst those bits of starch. And so slowly, if you get it hot enough, the starch expands and expands, it absorbs water and turns into a big kind of jelly lump. It's about 10 times as big as it was originally.
So when we make gravy, is this what's happening?
Well, that's what happens to start with. But then you get all these big lumps of kind of spaghetti all wriggling around. And then when you stir it, these big, long spaghetti-like molecules all tangle up. And as you try and pull your spoon through it, they all tangle up and sort of stick to each other and turn into a big kind of gloop.
OK, guys, do you have any questions about that at all? Ian, what about you?
I was just wondering, why when the gravy cooled, did it get thicker as well?
Well, in fact, if you cool the stuff down again, if you cool it down far enough, it'll turn into a jelly-like substance. And what happens is all these big bits of spaghetti, when they're hot, they're all wriggling past each other and they can tangle and untangle all the time. When they get cold, if they're tangled up, they can't untangle anymore. And so they all sort of lock together. You can stretch them, but they can't move past each other. It sort of turns into a really flexible substance, a jelly.
So is this rather like then when you put jelly in the fridge to make it set? Are we trying to do the same sort of thing, make it much more thick and just like a solid?
Yeah, a jelly works very similarly. Instead of starch, they use proteins, big long protein chains. But a jelly works very similarly. It starts off where all of the big long chains can move past each other when they're hot. When they get cold, they lock together.
So there you go. We've been explaining the science of gravy at Astley Cooper School in Hemel Hempstead today, so that's great. We've been using a microscope on the TV and Dave's massive brain with all the knowledge inside it. So thank you very much, Dave. Craig, Louise and Ian, it's been great having you help us. Did you enjoy the experiment?
Yeah, it was interesting, thanks.
Excellent. And yourself, Louise?
Yeah, made me understand it more.
Good. And Ian, I believe that was your first time making gravy?
Yes, it was. It was good.
First of many?
Yep, hopefully.
Well, hey, OK, he's going to be a gravy expert. That's great. OK, well, thank you very much. And join us next time for more kitchen science somewhere in the east of England. Goodbye.
Thank you very much, Derek and Dave, and everyone there at Astley Cooper School. You're listening, of course, to The Naked Scientist, Dr. Chris and Dr. Phil. We're here with you until 7. If you'd like to ask us any questions about anything science, 08459 25 2000, or you can email chris@nakedscientist.com. Phil.
OK, we've got an email here from Stacey in Toronto, Ontario, over in Canada. She says, "Hi guys, just want to let you know that I absolutely love your podcast, and I've gotten everyone I know totally addicted, whether they are fellow science nerds or not." Well, I wouldn't say we were all nerds, but fair enough. Just wanted to say thank you very much for the great Q&As. So cheers to Stacey.
I got one here from Alaska, actually, talking about exotic places. This one's from Danny, who's in Soldotna. I hope I've pronounced that correctly, Danny. She says, "Greetings from the state of Alaska. I recently discovered your podcast, and I want to tell you I enjoy it tremendously. The only was is I listen to it at work, and oftentimes my workmates ask me why I'm giggling. The only explanation I can offer is that I'm listening to an entertaining podcast, and that seems to satisfy their curiosity." Well, satisfying my curiosity now about insects, we're going to go over to this week's podcast pick. Petro has pulled out this week the MathGrad podcast from Chris Frederick, and he's going to be telling us about why insects are the size that they are.
Hello, this is Chris from the MathGrad podcast. Today I'd like to tackle the question, where are all those 100-foot-tall insects we see in the horror movies? The reason we don't see them is mathematical. Dinosaurs were able to grow to large sizes because they, like us, have an internal frame, which scales nicely as the size of the animal grows. Insects are an entirely different story. They have a skeletal structure known as an exoskeleton. This means their skeleton is on the outside of their bodies. They have hard exteriors which support the muscle and organs on the inside of their body. However, mathematically, when you keep the shape of an object the same, but increase its size, something strange happens. The ratio of surface area to volume decreases. This means the shape's volume and weight grows faster than its surface area. For an insect, this means the weight of an insect that must be supported by the exoskeleton grows faster than the exoskeleton itself. In other words, an insect the size of a building will not have enough exoskeleton to support the weight of the organs and muscle inside. Thus, there is a natural size restriction to the size which an insect can grow. And that is one reason there are no 100-foot-tall insects. Oh, and for everyone around the world who uses a system of measurement that actually makes sense, that is why there are no 30.48-meter-tall insects.
Thank you very much to Chris Frederick from the MathGrad podcast. There's a bit more information on his work at www.mathgrad.com. So if you enjoyed that, check out mathgrad.com for a bit more information about the maths of everyday life. Thank you very much, Chris. You're listening to The Naked Scientist. Dr. Chris, that's me, and Dr. Phil. We're here with you until 7 here on BBC Local Radio right around the Eastern Counties. And we're going to be talking very, very shortly to a bunch of guys about nanotechnology. And if you don't know what nanotechnology is, we've got the answer for you coming up very, very shortly. But you do have any questions, 08459 25 2000's our phone number to call, or you can email me, chris@nakedscientist.com.
The Naked Scientists, supported by the Wellcome Trust.
Dr. Chris and Dr. Phil here with you until 7 on BBC Local Radio in the Eastern Counties. Now, I'm talking now to David Carey, who's from University of Surrey. Good evening. Thank you for coming in.
Good evening,
Chris. Thank you for joining us. Nanotechnology. It's actually a term that gets bandied about in the media a huge amount, but people probably don't understand terribly much about what it means. So would you mind make it a little bit easier for us to understand?
Okay, so the whole idea of nanotechnology. Well, there are a couple of ways you can actually look at nanotechnology. The first way is called what we refer to as the top-down approach. In other words, we take things that are large and we try and make them smaller. And so that would be sort of very similar to what sort of commercial semiconductor fabrication companies are involved in trying to make transistors smaller, try to make them faster. And as I said, that's the top-down approach. The other way is sort of to use self-assembly and to allow the atoms or molecules or things on a nanoscale to do the work for you. So what you do is you arrange particular materials, you treat them in a particular way, such as heating them or applying energy to them, and by doing so they actually move around and they form, self-assemble into particular and interesting materials.
When we're talking nanotech, how big, though, is nanotech?
Well, if you sort of imagine the size of the planet Earth, and you imagine a football, and the ratio between the size of the Earth and the football is about 10 to the 8. If you then scale down a football by that same ratio, that'll take you to roughly the size of a C60 molecule, a buckyball as it's known as. If you go smaller than that, you're into sort of the whole area of sort of DNA and sort of single wall sort of carbon nanotubes, sort of an individual layer of carbon rolled up, that will form the sort of nanoscale. So it's really at the ultimate sort of scale of length.
And the reason that it's become a technology which we've embraced only recently, presumably, is because it is so small, so there are constraints with working at this scale.
There are lots of constraints. There are also lots of advantages of working at this scale. The constraints are how you actually can see these things, how you can manipulate or move them. But one of the key aspects, I think, is how you can sort of take the benefits of this nanoscale. When you get to the very, very small, two things really happen. The first is that, as we heard in the podcast earlier, the surface area to volume ratio changes. So basically your nanomaterial is all surface. So the volume plays much less of a role. The surface is the key. The other thing is that these very small scales, you're dealing with quantum effects. So this rather weird, unusual area of physics takes over, and you get unusual properties that you don't get at say, the bulk.
So they're not a nuisance, they're actually quite useful.
They can be very, very useful. In fact, there are a number of applications for them in sort of the biotechnology industry. So the display industry, for example, are very keen on using these sort of carbon-based electronic materials, carbon nanotubes, to extract electrons, use them in displays, for example.
Well, you're talking about displays. Are we going to get better television sets out of this?
Well, that's the ultimate goal. I mean, Samsung, for example, have developed a new type of cathode ray tube.
You better tell us what that is.
Yeah, absolutely. If you imagine your television, okay, and it's got a single source of electrons in the electron gun, what you can do is, as you try to make your television get wider screen, you also find that it gets deeper, so it gets heavier, it gets more expensive. The other way around, instead of having a single source of these electrons, is to have billions upon billions of sources of electrons. That means you can have these electron sources quite close to where the phosphors are, and the phosphors are the things that go red, green and blue on your TV screen. So getting them very close means that you have a very thin display. Thin display is potentially a cheaper display, but it's also lighter weight.
Yeah. So just explain the difference between, say, a plasma screen TV or an LCD screen and a standard television.
Well, an LCD or liquid crystal display essentially uses types of molecules that under particular conditions either allow light to go through or they block light. So they tend to be permanently on as a technology, and what you're doing is to make something go dark, you put something in the way of it. So inherently that's rather energy inefficient. Plasma screens, what you're doing is you're setting up an electrical discharge, and that tends to use very high voltages, and also therefore high voltages tends to mean your display becomes very, very expensive.
So how do you actually create that discharge? What's actually happening? If I could zoom in to the nanoscale on a bit of plasma screen TV, what's happening?
What's happening is you have a gas within a chamber, and you're setting up a high voltage discharge, which then breaks down and gives off particular colours, and that essentially, by modulating that high voltage, you're able to use that to glow red, green and blue, essentially.
So it's a bit like a strip light that's illuminating this studio, but obviously in a much more controlled way.
Yes, that's one way to look at it. But these things tend to be very energetically inefficient and power hungry, and you have to use very large areas of silicon as a substrate, and that's very expensive.
So how is nanotech going to make us have much better screens then?
Well, the idea is you can use materials which give off electrons very easily, such as what are called carbon nanotubes. Now, a carbon nanotube is, if you imagine just a single sheet of carbon atoms arranged in hexagonal rings.
A bit like graphite, then?
It's exactly like graphite. In fact, graphite is a layered material, and the layers are called graphene. And if you were to take one of those graphene layers and you were to roll it up, that would form a single-wall carbon nanotube. Now, you can have single walls of these, or you can have multiple walls, a bit like a Russian doll structure. These things, because they have a very high aspect ratio, when you put them into an electric field, they give off electrons relatively easily. Those electrons then hit off the phosphors, and therefore your television is red, green, or blue.
How do you make the different colours, though? Because I can understand how you can get the electrons out, but do you therefore have to connect the nanotube to something that glows a certain colour or gives off light of a certain colour when it gets excited?
What happens is the electrons come off of the nanotube, they are accelerated towards a phosphor in a straight line, and you just decide in your structure, one third of your screen will be red, one third will be blue, one third will be green. And it's all to do with the control electronics as to when the electrons turn on, when the electrons turn off. And that's how you, at different refresh rates, you get the different colours on the screen.
Can you just give us the idiot's guide to how these phosphors work? Because that's the coating on the screen, isn't it, that the excited electron hits and then encourages the screen to change colour.
That's right. There are different types of phosphors and phosphor materials, but one type of material is what are called the rare earth-based phosphors, and these are rather interesting materials. Most materials, when you shine light on them, will glow out different colours, red, green, blue, and a mixture. But the rare earths are rather unusual. When light hits them, they give off light in very, very well-defined wavelengths. And the narrowness of that wavelength is basically the narrowness of your colour. So you get a very, very clear image, very clean image.
Can we focus on these nanotubes? Because they really are an exciting bit of science, aren't they? Didn't Sir Harry Kroto discover these things? Got the Nobel Prize for making them or something?
Harry Kroto got the Nobel Prize for the discovery of C60, which is a molecule of 60 carbon atoms.
Right.
And this was partly when he originally was at Sussex, but he then went to Rice University and did some experiments with the late Richard Smalley. What happened there was they found the C60 molecules by hitting a laser into graphite. Carbon nanotubes came about and were discovered by Professor Ijima in Japan, to some extent by accident. He was trying to do a similar experiment, and he looked at the material that was left over, expecting to see these C60 molecules. That's what he was interested in. And to his surprise, what he found were these long helical structures made out of just carbon atoms. And he then sort of wrote this paper up into Nature, and it's been one of the most highly cited research papers since 1991, and it's developed the whole field of carbon nanotube electronics.
Okay, so that's electronics taken care of, and I've got a little question about these nanotubes for you in just a second, but that's the electronics industry taken care of. But obviously nanotech is a much broader field than that, so set the scene for other things that people are doing with it.
Nanotech and nanotechnology and nanomaterials, they can be used in a number of different areas, particularly in the area of catalysis, sort of enhancing reactions. They can be used in fuel cells. There's a huge patent portfolio on using nanomaterials for cosmetics. They can also be used...
Really, how?
Oh, a lot of various cosmetic companies have actually... If you think what a cosmetic is, you're dealing with material that you rub onto your skin. Now, if you think of things like sunscreen, 5 years ago, sunscreens were all sort of coloured pigment. Now, if you look at a lot of sunscreens, they're actually clear. And that's because the size of the material, the titanium dioxide material, has got smaller and hopefully will improve the response and protection towards the sun. But there's a whole range of these nanomaterials that are beginning to emerge in sort of unusual areas such as skincare and things like that.
Exciting, smooth stuff. We're listening to David Carey from the University of Surrey. We're also just going to be talking to Donald Fitzmaurice in just a second. If you'd like to join our conversation this evening, 08459 25 2000, or you can drop me an email, chris@nakedscientist.com. We're live right across the Eastern Counties on BBC Local Radio. Coming up shortly, also Stephen Webb from Daresbury Laboratory in Warrington is going to talk about how biology is meeting physics, literally watching behaviour of cells that could become cancerous down a microscope. How are they going about their business, and what can we do perhaps to stop them? And Neil Morgan is from Cambridge University. He's going to give us a solution to smelly socks, we hope. That's all coming up shortly. But first of all, let's find out about a very interesting application of nanotech from Donald Fitzmaurice at University College Dublin. And that's powering the next generation of microprocessors, potentially with DNA.
Indeed. Well, maybe I'll just back up a little bit and say why we want to do this type of work. Every one of us has got used to going into our local computer store and buying a PC that's twice as powerful and half the cost compared to the last one we bought just a few years before. And that's a huge achievement by the electronics industry, where they're able to deliver improved performance at reduced cost year on year. And that's governed by something called Moore's Law, where the number of transistors on a wafer doubles every 18 months.
In other words, the processing power, the number of transistors doing the computing power on the computer chip.
Right. And the reason why that works is because if you want to do a computation in a computer, you've got to move electrons around. And if you want to shorten the amount of time it takes to do a computation, then you've got to bring everything closer together. And the way you bring everything closer together is you make it smaller and you shrink it and shrink it. Now, that's been going on now for almost 4 decades since Gordon Moore first observed this, and it's a huge achievement, and it's really underpinned a revolution in the way we do everything in our lives nowadays in certain parts of the world. But for Moore's law to continue, for us to continue to be able to increase processing power at this rate, we're going to have to continue to keep shrinking the bits that make up a computer. And that presents us with 2 problems. One, making stuff that small is really hard and very expensive. And secondly, when you move electrons really close together, they start to know about each other. Okay.
Quantum effects.
Yeah, you get quantum effects and also you get power density effects. So the effective current inside these things goes way up, and the power density inside a Pentium 4 processor is approaching something like the power density inside a small star.
So quite literally, I mean, to put this into plain, simple terms, what you've got is one tiny component here getting so close to the second component here that the two begin to interfere with each other. And there's therefore a theoretical limit to how many of these things you can pack onto one computer chip.
Exactly, and you've lots of electrons in the one place and they're all repelling each other, and you have to produce you need a lot of energy to force them through, right? And the amount of energy you're putting into one small space is so much that it's something like the amount of energy you find in the same volume in a star.
So does this mean then, Donald, that in the near future we're looking at a theoretical maximum processing power given current technology?
Well, there's the so-called industry roadmap. And the industry roadmap predicts the rate at which processing power will increase. In other words, how fast the bits of a computer will shrink. And what they believe is that they can continue to have the size of a transistor every 18 months for about the next possibly 10 years maximum, out to about 2012, 2016. And then the industry hits what they call the red wall. They just don't know what's going to happen after that. So all the big semiconductor companies and lots of other types of companies are interested in, well, how could we develop different ways or different approaches to making electronic devices that would get us around these problems of it's very hard to make stuff really small, and at the same time they start to talk to each other and they have huge power densities.
So what's the answer?
Well, there's 2 things. One, you have to think of new ways of making them fundamentally, and one, when you look around in the world we live in, you find that biology is very good at making lots of things that are very small and packing them very close together and getting them all to work together without interfering with each other. And the way biology does that, it starts with atoms and assembles them into molecules, and then assembles the molecules into collections of molecules and into larger collections of molecules with a hierarchy of function, all integrated. And of course, you see this every day in your life. You have a shave in the morning and you cut your face and you come back 24 hours later and that cut is gone. Well, millions of operations have taken place, right, to remove the damaged cells, to clear up any infection, to build new cells, to pop them into exactly the right place.
Well, to grow those whiskers in the first place.
Exactly. And let's say that finger's that cuts on your finger. Not only does it repair the skin, but it puts exactly the same pattern in the fingerprint back. So it's really remarkable. So there's a lot to be inspired by from nature.
Okay, so you're advocating borrowing from biology, but obviously translating from a cut on a face to a computer chip, it sounds challenging.
Yes, so we're working closely with our colleagues in University College Dublin and a number of colleagues at the Centre for Research in Adaptive Nanostructures and Nanodevices, CRAN, in Trinity College Dublin, and particularly closely now lately with the folks at Intel and various other companies. And what we're trying to do is we're trying to combine the best of both approaches. So we're using conventional methods from the semiconductor industry to build really smart substrates that will help us organize molecules, and then we're taking lessons from nature, and what we're doing is we're building molecules which organize on that substrate and then which assemble nanoparticles of metal and semiconductor and insulator into the right place and build the devices we want.
Okay, so literally you can use other molecules that know how to have a shape and a structure to move other particles into just the right place to do something useful.
Exactly.
So if you focus in on DNA, for example, we know it forms that rather nice helix, and if you have a certain sequence of DNA, it forms other structures as well. I presume that's where you're going to go with this.
Yeah, one of the things that's very nice about DNA as a potential molecule, as a basis for this approach, is a number of things. One, it has intrinsically got information stored in it in the form of the sequence of base pairs, and that's how biology stores information about its own future and its past. Secondly, you can produce DNA in any sequence virtually at the touch of a button in a modern laboratory. The whole process is automated. So it's not only an attractive molecule from an intrinsic point of view, but it has the potential to be scaled industrially if you ever wanted to do that.
But is this actually doable, Donald? I mean, the idea of actually getting DNA to organise molecules in just the right place to make an electric circuit sounds like a great idea, but it sounds pretty difficult.
It is. Have
you actually tried this yet?
We have tried this, and indeed a number of other groups around the world have tried it, and there is growing success in this approach. So much so that companies such as Intel and various other companies are now actively exploring this approach and pushing a lot of resources into it.
You've always got a living chip there, haven't you, then?
Exactly, and I mean, let me just explain to you one or two of the things that have been done. I suppose the simplest experiment that has been done is you take a conventional electronic substrate, which say has somewhere where the electrons come from and go to, and conventionally you might connect that up with a piece of metal. But now you're connecting that up with a piece of DNA, which is just the right length, which swims through a solution, sits down on the surface because it recognizes the place on the surface it should sit for various reasons. And then you build nanoparticles of, let's say, gold or copper, whatever it happens to be, and they know how to recognize a certain part of the DNA, and they sit down in a line between the two electrodes, and now you can pass electrons from one end to the other.
And it's much quicker because it's much smaller. But how much smaller do you think this will... how many years of technology will this buy us?
There's two things. One, in principle, it should be possible to build very small wires, but also, and this is more important, I suppose, it's in principle possible to build lots of wires in parallel very inexpensively. Because there's two problems here. It's not only what you end up with, but it's how hard it is to make it. So this approach offers the possibility of building new things with new function that overcome the power density and the interference problems, but it also offers the way of making things in massively parallel approach. And I just basically give you an idea about that. Let's say you put molecule A and molecule B in a beaker. So you have beaker with molecule A and you have beaker with molecule B, and you pour the two into another beaker, and they form a new molecule, molecule C. Well, if you have just 100 mils of each, you can be making something like 10 to the 27 new molecules in a few minutes.
One with 27 zeros after it.
Yeah.
Probably more than there are stars in the known universe, actually.
So you can, in fact, in principle, using this approach, you could make more transistors in a few minutes than have ever been made in the history of humankind before. And I mean, whereas 10 years ago that was seen as very fanciful talk, and, for good reason, because the problems facing us were very significant, groups around the world like Jim Heath and Fraser Stoddard, Chad Merkin, ourselves, various other people around the place, have made, in each of our own slightly different approaches, enough progress to make this, at least now, a possibility. I wouldn't for a second suggest we're there. There's a huge amount of work yet to be done, and it's still a great challenge to turn this into a commercial, scalable technology, but it's no longer one that hasn't got a chance.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
It is Chris and Phil here with you until 7 on BBC Local Radio right around the Eastern Counties as the Naked Scientists this evening, talking the science of nanotech, in other words, the science of the very small. Stephen Webb is from Desborough Laboratory in Warrington. Good evening, Stephen. Thank you for coming along.
Good evening.
Tell us about your work, literally zooming in and seeing things at the microscopic level, cancer in action.
That's right. In many cancers, there's a molecule called epidermal growth factor receptor that's involved. You may well have heard about Herceptin in the news recently. That's involved in one of a family of 4 molecules, of which epidermal growth factor receptor is one. What happens in order for the cell to divide is that a signal has to come in the form of a molecule from another cell. And this molecule attaches itself to the epidermal growth factor receptor on the cell membrane. And when that happens, there is a change of shape of the receptor molecule. Now, it would be possible, if we knew exactly what the change in shape was and how it progressed in time, for somebody else to take this knowledge away and design a drug which prevented it.
In other words, just block up the receptor,
basically,
the docking station, so that the cancer cell doesn't hear that signal.
Mm-hmm. This is a normal process. It happens in all our cells anyway. It's just that it basically goes into overdrive in cancers.
So what we can do to exactly see what this change of shape is to attach little fluorescent tags to different parts of the receptor molecule. There are things like something called green fluorescent protein, which has been extracted from jellyfish.
Yeah.
You can stick that into the molecule. You can attach, for example, quantum dots, which are little cadmium selenide molecules, which are which have the very small little nanoparticles which you can tag on to different parts of the receptor molecule. Or you can use more traditional dyes with names like Psi5 and Psi3. If we excite them, for example, with a laser, they will then emit fluorescence. And the wavelength of the fluorescence that's emitted and the polarization of the fluorescence that's emitted gives us information both on distances and angles between different fluorescent tags on different parts of the molecule.
So you can begin to build up a three-dimensional picture of what this docking station, this receptor, looks like on a cell surface.
That's right. We can see. The idea is that in real time we can see exactly the changes in shape that are occurring in this molecule.
And what about if you throw this drug on? Does it tell you about how these drugs, or the natural thing that wants to lock onto that docking station, what happens to the receptor when they're present?
Exactly. That would be the idea in the future when future drugs to develop to prevent this thing happening. I mean, Herceptin only works on the ERB2 or HER2. It's got two different names of this family of 4. There's actually 4. They're all involved in different cancers, and we want to study all of them, not just the ERB2 receptor.
Okay, so you've been able to label these independent bits of the receptor in order to see how they all interact, but how is this going to translate into a new version of Herceptin? And in what sort of timescale? Why is this better than the traditional way of doing things?
The receptor molecule itself, the sort of exact structure of it has been studied using methods like X-ray crystallography, and that gives you an idea, a static picture of what the molecule looks like, and it tells you what it looks like just in solution rather than in an actual cell, which is a completely different thing altogether. So what we can do is in live cells, and we can do it in real time. So hopefully this would be, if you like, it's a quicker method and a more physiological method of getting the basic science that's necessary in order to design the drug, which could then be done using. You could study how the drug was working, possible different designs. You could study how good they were using these microscope techniques as well.
You're listening to The Naked Scientist. Dr. Chris and Dr. Phil here with you on BBC Local Radio right around the Eastern Counties. We're joined this evening by David Carey from the University of Surrey, Donald Fitzmaurice, who's come in from University College in Dublin, Neil Morgan from Cambridge University, who's going to be talking to us shortly about smelly socks and how nanotechnology can help solve that problem. Pity Kat's not here this week. She's not here to defend herself, so I can say what I like. And Stephen Webb there, just talking about their new way of looking at cancer cell receptors, for example, under a microscope and tracking what they're doing, and therefore providing scientists with a way to make better drugs. Let's have a quick chat to Ariane, who's on the line. Hello.
Hello.
Good evening. Thank you for joining us. Where are you calling from?
Cambridge.
Oh, well, good evening. What's your question?
Well, what is the science behind a hologram?
Ah, fantastic. Right. Now, we have some of the finest brains in light science and nanotech here. Come on, you're looking pretty promising, David. Come and tell us what a hologram is.
Okay. Oh, it's been a while since I've done anything with holograms. Essentially, a photograph, for example, as we know, is essentially just a 2D image, and you can look at a photograph. Camera takes an image which is inverted onto some sort of photographic film. With a hologram, you essentially can you look two views of the perception. So you can often do this with lasers, and you can aim the lasers at the particular figure, and it's the interference effect which is then recorded. So this is often found in things like your credit cards often have holograms, and you can also get holograms in various passports and other types of identification. And one of the interesting aspects is whether holograms will take feature in any part of the national identity card system, which the government are thinking about.
Are they very copyable?
I'm not absolutely sure. As far as I know, I think it's very difficult to copy a hologram in one sense, because you need to have this dual perspective of the person whose image you're trying to copy. But ultimately, any of these decisions as to how easy or difficult it is depends on who's going to be looking at the faked or the copied hologram, whether it's a human being or whether it's some sort of automated device. So then you're down into how good is the copied hologram relative to some sort of detection system.
Does that answer your question, Ariane?
Yeah, pretty much.
Well done, David. Do you want to have a quick go at the quiz?
Yeah, sure.
Okay, got tickets up for grabs tonight to Kew Gardens. Have you ever been there?
No.
Well, it could be your first time. You ready?
Yeah.
Ethylene glycol, that's ethylene glycol, is the chief ingredient in alcohol. Is that science fact or science fiction?
Science fact.
Sorry, unfortunately not.
You can have one of these.
Yep, ethylene glycol is actually antifreeze, and is actually really poisonous, so definitely don't drink any.
All right, have a go at this one. Bronze is an alloy of copper and tin. Is that science fact or science fiction?
Yes, science fact.
Oh no, sorry again. That's in fact those two things. Copper and tin actually make brass. Bronze is actually a mixture of copper and zinc, so close but not quite.
I'll tell you what, though, it's a fantastic question. So if no one else beats you, I'm going to give you the tickets anyway, OK, for such a good question. All right?
Yeah.
Thanks for joining us on The Naked Scientists.
Laying the facts bare, The Naked Scientists.
Dr. Chris and Dr. Phil here with you as The Naked Scientists. If you'd like to ask us a question, we're talking nanotech this evening, 08459 25 2000, or you can email me, chris@nakedscientist.com. Now, you've all been waiting for this, the nanotechnology behind smelly feet, but no, tell us, Neil, there is a serious side to this.
There is, yes. This is basically to do with nanoparticles and, more importantly, functional nanoparticles. A group in ETH Zurich, which is a university in Switzerland, basically came up with the idea of mass producing lots of silver oxide nanoparticles. Now, these are basically very, very tiny particles of silver oxide.
How tiny?
We're talking anything from a few molecules up to a few thousand nanometers. So basically, we're talking billionth of the size of your coffee cup in front of you here. Very, very, very tiny particles.
Okay.
But the purpose of these particles being so small is that their surface area to volume ratio, as has been mentioned before, is incredibly high. So they're incredibly reactive. And silver itself is very, very good at basically killing bacteria. So the idea of the spin-off company was to mass produce tons of these silver nanoparticles, which would then be put into socks, and then when you put your socks on, the bacteria which would cause the nasty smells would basically be killed off, and hey presto, you don't have
few
smelly feet.
Facts for you.
Indeed.
The average person sheds about 40,000 skin cells every single minute, which, if you added that lot up, would over the course of a lifetime weigh about 3 or 4 stone in dead skin.
Ouch.
And the sweat glands in your feet squirt something like 1.5 litres of sweat into each of your shoes on a roughly daily basis. So if you put the two together, you've got a pretty stinky combo.
Indeed.
It's interesting about silver. Do you know why it has this profound antibacterial effect?
I'm afraid I don't specifically know why, but I know that certainly lots of companies are investigating this, and I believe one of the big plaster manufacturers has started to put silver into their plasters for specifically that purpose, to basically make very specifically antibacterial plasters, so for cuts and grazes and the like.
It's easy to think of this as a new technology, but it's not, though, is it? Because there's evidence the ancient Egyptians knew about this, because they used to put silver in some of their drinking water, because they knew it used to kill bugs, and of course waterborne illnesses cause a hell of a lot of problems, especially in hot places where you've got sun, people, pollution all come together, and you end up with food poisoning.
Mm-hmm.
So tell us about these socks a bit more. How do you actually attach the silver particles onto the fabric so that when you put the socks through the wash that they don't all fall off?
Well, I believe the particles themselves are then incorporated into the dyes, basically. So you'd mix those up with the dye products, and they become basically suspensions of these particles. And then when you spray that onto the fibres, they become basically intertwined with the cotton fibres, say, in your cotton socks. And that's why they don't just fall out and you don't just get little dust piles of silver nanoparticles in the bottom of your shoes.
Because one other sort of spin-off of that, I heard someone saying they were going to make paint which could tackle smoke problems. So if you had a pub, obviously a lot of people are smoking there, not for much longer if Tony has his way, but you got a lot of people smoking in a pub, and they had this paint which you could paint on the wall which would mop up and neutralise tobacco smells. And someone else suggested that a sports bag could also be treated in the same way as your socks, to neutralise your kit rather offensive odour after a vigorous game of rugby or something.
Indeed. And there was research I was reading on, in fact, on the BBC Science website the other day, where an Australian group has developed a new form of titanium nanoparticles, which are doped with another chemical, I think vanadium. And in a similar way to the self-cleaning glass that you may have read about, which Pilkington have developed, basically the way the self-cleaning glass works is that you have a very thin layer of titanium dioxide on the surface of the glass. This becomes very highly it can basically oxidize chemicals very, very rapidly under the presence of UV light. Now, obviously, that's all very well and good for glass, for window panes, which are exposed to natural sunlight. But this Australian group has basically developed, they've shortened what's called the band gap, which basically is what frequency of light makes these particles active, and basically reduced it down to light frequencies which are very similar to the natural lighting in your bathroom.
Right.
So, for example, basically, if they can develop this technology further, you basically get paints and tiles in your bathroom that are self-cleaning under your bathroom lights.
Now, wouldn't that be fabulous? My wife would be delighted with that. Right, I've got a quick question here for all of you. This is from Tristan, who's in Melbourne, Australia. Very, very quickly, he says, is it possible to make carbon-60, that's these tiny carbon molecules that we were talking about earlier, these buckyballs, using typical items found in a household? I've heard that C60 can sometimes be found in soot and ash from a fireplace. Is this true? Who wants to have a go at that? David?
Making C60 is actually in a laboratory not too difficult, but as to whether you can actually do it with soot and fire, I'm not entirely sure. The way we normally do it is we strike an arc between two graphite rods, and we look at the debris, the soot, essentially, of that.
When people were studying this, didn't the sales of welding kits go through the roof? The scientists were trying to make C60.
Absolutely. I mean, all you essentially need is something that produces a high amount of current, and preferably at low voltage, so it's actually relatively easy to do. But it is found in the soot of arc discharge from graphite. Whether the temperatures are high enough in your fire, I'm not entirely sure.
Sorry, Tristan, so you can't make C60 at home necessarily, but go and buy yourself a welding kit and you might be able to. Christine's in Norfolk. Hello, Christine.
Hello.
Thank you for joining us. We're going to have to be quite quick with this because we've got about 2 minutes left, but what was your question?
I just wondered how you get a radio signal back or pictures back from a spaceship, sort of 9.5 years out into space.
Right, well, it will take a long time. I mean, if you think that New Horizons space probe that Christine's talking about, Phil, it's going to be in the vicinity of Pluto. Light itself takes, 6 hours to get back, so presumably a radio wave will too.
Yep, absolutely. A radio wave takes... radio waves are just a different type of light, essentially. So they travel at the same speed of light. So, again, 6 hours to get back. Now, the way it's going to work with the New Horizons probe is that the mission itself includes a really big radio dish. Again, just like the radio dish on your house, but quite a lot bigger. Now, it takes a lot of power to fire the radio signal all the way back, but essentially, yeah, it's just a big radio dish, transmits the radio waves back to Earth, and a big radio dish on Earth to collect them again.
I hope that sort of clears that one up for you, Christine.
Just a little bit. I'm just wondering why, being an amateur radio enthusiast, I can't get as far as what they do if they've got...
Unfortunately, and I'm going to have to sort of wind it up because we're running out of time, but the reason for this is that on ground we've polluted the radio spectrum with so much noise now and other radio signals, everyone ends up interfering with everyone else, and it's whoever's got the strongest signal that wins.
Oh, right. So in other words, if you've got a bigger dish, you can get through.
You certainly have. The bigger is better in the world of radio. Thanks very much, Christine. We've got to leave it there because we've run out of time, but I have to say a huge thank you this evening to David Carey from the University of Surrey. Thank you very much, David.
You're welcome.
To Donald Fitzmaurice from University College Dublin in Ireland, Neil Morgan from Cambridge University, and Stephen Webb, who came in from Daresbury Laboratory in Warrington. Thank you all very much indeed. Next week, we're going to be looking at the science of recycling, where your waste goes and what it ends up as, and also we're going to be giving you the recipe for biodiesel, so tune in for The Naked Scientists at 6 next week.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.